Thank you for the invitation for this virtual seminar series for your summer of chemical theory. And hopefully with this talk, I will be able to kind of lighten up your neurons for understanding, basically get into the metal oxide chemistry and further studies and investigation in this space. So what I'm going to talk about is basically try to understand descriptors in metal oxide surface chemistries and use these descriptors for discovering new electrochemical devices and reactions. If this works, I have to just go with the different pointers. Sorry for that. Point option. Okay, so let me start with a little motivation. And the motivation is still the same as it was basically with this original work by Jens and Thomas Bligard, that if you want to achieve sustainability in the future for the planet, we still need to store the energy from sunlight in some very dense form, which is by far the best way to do it, as the nature is doing it, into chemical bonds. And as you know, there is the chemical energy is stored through wind, water, solar, or plants, or directly, but that doesn't really matter how is it stored. But actually, we have to kind of from these from these sources, we have to store it all the way to these useful molecule, energy dense molecules in the chemical bonds. And there is various pathways. It can be direct catalytic, thermocatalytic, electrocatalytic, photocatalytic. Even the source of the energy can be a little bit different than solar. It could be nuclear. Nevertheless, we still have the problem that this storage of energy and conversion of the energy and creation of these valuable chemicals have to be more CO2 neutral. It has to be basically sustainable. And with that, we need to focus on development of catalysts, because each of these processes requires a catalyst to store the energy and enable also, for example, creation of hydrogen fuels. So these catalysts, however, there are very strict criteria for these catalysts. They have to be very active. Actually, they have to be very efficient, much more efficient than naturally occurring in regular naturally occurring compounds. And they have to be also very stable and durable, so they can perform the operation for a long time. And they have to be cheap. Also, basically, they have to be air abundant, so we can apply this technology on a large scale. Now, we have a problem, and the problem is that if you look here on the natural abundance of the elements in the upper Earth crust as a function of atomic number, we see that on the logarithmic scale that only light elements are abundant. But if you want to build a catalyst from these elements, it doesn't work very well. So we need to really go look down the periodic table. But those heavy elements, which are good catalysts, are much less abundant. Also, what you can see actually, that this kind of a decrease in abundance, there's also this zigzag behavior, kind of an odd and even kind of a scheme. Anybody knows why is that? Well, that's naturally because when the elements are forming in the planets, actually in the stars, the number of neutrons and protons has to be preferred when it's even than when it's odd, and therefore you have more stable elements with an even number of nucleons. And so you can see as you move from rock-forming elements to 3D metals to the rare earth metals, actually rare metals are not that rare. Much rarer are the rarest metals are these called platinum group elements. And why they are actually so rare? Well, the reason is very simple, that they are actually dissolved and there are natural impurities in iron. And when the planet was forming, the melted iron actually became a melted core of the planet, and these elements are actually part of this melted core, and they are not in the upper crust. So that's very unfortunate, because we have very few of these elements. And to make a situation worse, iridium is one of the rarest elements out of the platinum group metals, and is actually naturally occurring impurity in platinum itself. So there is one exception, however, and that's meteorites. So because meteorites, it's a giant chunk of melted iron. It contains actually lots of iridium. Has been, for example, this big example of Willamette meteorite in Oregon. So, but that's only exception. And as a rule, it's very hard to achieve iridium production, which is one of the best and most durable catalysts for water splitting, which I'll talk about a bit later. And this is now used for all the hydrogen production for basically acidic hydrogen, PEM, hydrogen production on the planet. And yearly production of iridium is only 1 ton for the whole planet. And as a result, it's very expensive. And typical electrolyzers need several hundred grams or even a kilogram of this material. And you can see the cost of it. So basically, iridium is slowly becoming like a special spice needed for hydrogen economy. And there is a race to get more of it by all the nations around the world. So to solve the problem of iridium and other platinum group metals, we actually in our group at SUNCAT, we're developing various theoretical and experimental approaches. And I am part of several studies, for example, studying general trends in transition metal oxides, their catalytic activity, and try to mimic iridium and platinum group metals for various reactions such as oxygen evolution, oxygen reduction. Also, we are trying to develop descriptors in connection with machine learning to find some kind of a trends in the series, and also can we actually find abundant equivalents for iridium metals and platinum group elements. And this is what I'm going to be mostly talking about today. But we also have lots of other activities, such as trying to create single atom catalysts or completely eliminate transition metals from their catalysis. We also do lots of operandi studies. Now, we also, our research is also plugged into a bunch of applied centers. So one of the applied centers is a Liquid Solar Alliance hub, which is in charge of developing solar liquid fuels. And it's centered around Caltech and Berkeley and SLAC, for example, where we are looking for series of kind of optimizing activity and stability of transition metal oxide for solar fuel production. We're also studying CO2 reduction. We're studying reactions beyond oxygen evolution reaction, for example, for battery application and metal air batteries, which also I will kind of quickly touch on. And we are developing new theories for catalysis. Of course, this is only 1 hour talk, and it should be also entertaining. So today, the main theme of our talk, of this talk, will be discussion of the new activity descriptors. So why do we care about descriptors for the metal oxide? So as we know, metal oxides are the most abundant types of materials on planet Earth because of the oxidizing atmosphere. Most things oxidize and they are very stable, and they form majority of the compounds. And they are also very catalytically active for all the oxidative reactions. And so the history of the decades of research, people try to understand the catalytic activity in the systems. And so they develop basically a series of very quantitative understanding of this activity trends through basically some kind of a measured or calculated quantity or proxy. So they try to measure the bond order or bond energy, or directly calculate the bond strength or change the bond strength. That led to a series of basically volcanoes, which is understanding the overall activity trend. As the bond gets stronger or weaker, we kind of reach the maximum of the activity. Now, on the bottom part of this decade-long plot, we can see additional alternative approaches where the idea was to take a proxy or correlation or descriptor, which is not directly related to bond strength. It's just indirectly related and correlated with the activity. And this was pioneered by Sergio Trassati, which was the Italian electrochemist, famous electrochemist, who came up with this idea of volcano for oxygen evolution reaction, where he correlated the activity of the metal oxides for oxygen evolution with the heat of formation of the metal oxide. Then there was the development of D-band model by Hammer and Norskov, which basically tried to attempt the activity of the transition metals for example, oxygen reduction with position of the D-band center of the transition metal. Later on, this was expanded in kind of a more generalized way, where you can just start to, rather than looking at the position of D-band, you can look at the filling of the band. In the case of perovskite system with Suntivich and Schwarzschild-Horn, it was the filling of the EG and T2G bands. So basically, filling is somehow responsible, is an indirect measure of the activity of the perovskite material. This was also expanded to just counting number of out-of-the electrons by Calle-Vallejo. So you can take a series of metal oxides and you can just keep calculating number of electrons, and for given oxidation stage, you get kind of a linear trend in activities. So this is just counting number of d electrons, but we can also count p electrons or look at the p band center. So that's what we did in the study in 2019, which also worked pretty well. However, you can see there are two distinct approaches. One of them, the upper one, is to realize a calculation of the explicit bond order or bond strength, and the bottom one requires calculation or observation of some external quantity, which is not directly measured at the bond level. So this is interesting, and so in order to measure this in 2023, we thought that it's interesting that there's the unifying theory, which is both qualitative and quantitative at the same time. So for that, we needed to make a very accurate data set. And so what we did is we selected rutile transition metal oxides, which exist in variety transition metals, and we calculated 3D, 4D, and 5D series. And we cut it two main stable surfaces, which is the 110 and 100. And on this arrow position, we calculate the absorption energy of oxygen and OH. And when we did for the oxygen, we found out that as we align these elements across the series, and the dark blue is for 110 and the light blue is for 100, you can see that there is like at the groups number 4 and group number 14, which are the fully occupied states, you have a very big absorption, and then you have like a sharp downtrend and another sharp downtrend. So there are two distinct minima, or kind of a global maximum absorption energy. And this is what we identify as a high spin minima, and the second one as a low spin minima. And this very strong absorption energy corresponds where the absorbate and the active site achieves this kind of a D0 state. And when we did it for 4Ds and 5Ds, we found out that this trend is kind of a similar, except the high spin minimum goes away and everything is low spin due to much stronger crystal field splitting. And therefore, that basically high spin is suppressed and it's only active in the weak crystal field splitting. And again, we found out that this strongly bonding region, actually vanadium, niobium, titanium has the strongest absorption energy related to this D0 order for the oxygen absorption. And overall trend is that there is much stronger coupling for 4D and 5D than for 3D. We also did this for OH, and the answer was essentially unchanged. And we also had a previous study for example, for layered oxyhydroxide, which were in the +3 and +4 oxidation state. And we also have some perovskite studies from previous calculations. And when we actually just extracted the +4 3D elements along the same series, we saw the same high spin minimum and low spin minimum, and also centered around vanadium. And also we found D0 at titanium and germanium. So this was very interesting and saying, wait a moment, there is something very similar in all these systems. There must be a descriptor which can describe this activity with a single theory, right? Very, very accurately. And this wasn't the whole story. So actually there has been I started reading much of old books, and there was this old kind of a plot showing it by Doden, and he calls it double peak volcano of 3D reaction rates of metal oxides. So he shows 16 different reactions on transition metal oxides. For variety of these oxides have different oxidation states. So it's not just +4, it's also +3, +2, and so on. And if you just count number of the electrons, basically in occupation of this transition metal and these oxides, and you align it, sorry for that. If you align it across the series like this from D0 to D10, you find out that they always have a weird maximum in some region. And so we just took our data and plot it the same way, where now there's this overpotential, which is basically O minus OH energy from the previous plot I showed it to you. And again, you can see that the 3D series has two maxima, one around vanadium, chromium, and one around cobalt, where there is so-called high spin and low spin minima. So basically, the conjecture is that though there's double peak in 3D rates in these different 16 reactions must be due to the different minima for 3D elements having a high spin and low spin for special descriptor. So if for auto spinning is O minus OH, but for these different reactions, a different quantity. Nevertheless, there is always a high spin and low spin for 3D. While this high spin peak gets suppressed in 4Ds and completely suppressed in 5Ds, and then only a single peak remains, which explains why ruthenium and iridium are the most active +4 elements for oxygen evolution reaction. So this was kind of a nice, and we got encouraged by that, and we said, okay, let's look at this underlying theory. And actually jumping forward, so there was also another published data set, original set for OR rates by Santovic and Yaksha Horn, which shows that there was also double peak in rates for ORR reaction in these perovskite materials, while they use kind of a proxy for this number of d electrons, which was in their case was the EG minus D2G filling. So you can see that there are always two maxima, which vary. The first one is the high spin and second one is the low spin. And it's only for 3D elements. So encouraged by that, we said, okay, there must be a quantity which can couple this quantitative and qualitative understanding together, so we can explain once for all the reactivity in the 3D, 4D, and 5D Ruth-Al series. So we looked, we tried several approaches for several months. Nothing worked. Again, we tried various proxies, and then eventually Benjamin, who is my postdoc, he actually came up with a proposition that we should look into the lobster code. So what is lobster? Lobster is a code which, on top of your projected density of states, you can calculate so-called crystal orbital Hamiltonian populations. So why is that important? Because that allows to calculate the crystal Hamiltonian populations between the oxygen P states and transition metal D states to a single quantity through this kind of a projection of the local orbitals on that bond. And it's a bond specific. So how does it work in practice for metal oxides? So we actually, for each active center, here you see like the metal oxide octahedron, and you can see a transition metal center, oxygen 2p state. This is an example of ruthenium O2 or oxygen there. So for this particle bond, we can calculate the projection between the d electrons and oxygen 2p electrons, which of course split to T2G and E2G bonding, anti-bonding states. And we just simply sum them up to the Fermi level, which we call the integrated COHP, which will be just called for the rest of the talk just COHP. And this integrated COHP kind of goes over the maximum and then decays steadily to zero. So as we're adding more anti-bonding state, basically it's back to zero. So the maximum is always for the maximum bonding state. So it's an overall measure of how much bonding, covalent bonding, I can achieve in the transition metal oxides. So the COHP code is basically commercially available. It's a part of routines for VASP, for example, and it can be directly projected on all the calculations. When we did it for the series of transition metal oxides, and these are the bulk levels, so these kind of look like a density of states, but these are these integrated plots. And you can see that as we're going up and up in the series, then we are adding more and more anti-bonding states, and we are moving basically on this ICHP plot towards the full filling. So basically the filling of zero when we're adding all the bonding, anti-bonding. And we would say that when we are close to this maximum, to the black belt, when we are telling that's when we have maximum of the only bonding states. And you can see how it is decaying. And now if you look at the 4D and 5D series, it's very qualitatively similar, except the overall area for the bonding is getting increased. So this explains why the bonding is generally stronger in 5D and 4D elements than in 3D, because you have simply more covalent bonding available for a given group. And then, so you are basically steadily shifting up. And overall, there is still the same behavior that you're adding the anti-bonding states. We really like this plot. Now, can we use it for some qualitative prediction? So actually, one thing, additional approach is that we can actually decouple kind of a filling out of the whole thing. So we're just looking how the overall maximum is moving relative to the Fermi level position, then you can subtract that, and the result difference is this filling. So basically just confirmation that really the difference is related to the filling, and this is how many anti-bonding we are adding to the overall system. So we go from no anti-bonding to fully filled states, full anti-bonding for these late elements. So can we use this for some sort of qualitative theory? And it turns out that yes, we can. So we can literally take the ICUHP energy for metal-oxygen bond. We can take, and so in brutal systems, they are very equivalent. So if we just take a single bond and we extract it from the bulk, and we can get this kind of a quadratic relationship for OH and O. And there are some notable outliers, which is, you can see here, titanium, zirconium, hafnium, which are at the beginning of the series, and they have 0 d electrons. We can also do it for the surface alone, but actually in this original study from 2022, we concluded that bulk is sufficient and the errors are actually even smaller because there are some additional errors, for example, for this high-spin state. And so we said this is a very viable way going forward, and we should just look into bulk. We should just neglect these D0 states like titanium, zirconium, hafnium, and go forward with the accurate theory. However, that wasn't good enough for us, so we continue. And in next work, we started looking in more detail. How is this changing if we go beyond single site? So remember, in the original approach, we just took a single bulk or surface bond, single CHP for this active site between the projection of the d electron and 2p state of the oxygen. However, we always knew intuitively that crystal field theory tells us that we should be considering a crystal field of the whole active site. So all these 6 octahedron, the octahedron has 6 oxygen bonds, so we should be adding it together. So how does that look like for the D0 systems? So as I told you, the titanium, zirconium, hafnium, those were the outliers. And when we look at the outliers, we find out basically there's a steadily increase, but it's very small. And they are basically constant, and they look the same like in the bulk, also in the slab. So that must mean that this CHP is not really changing at the active site. And the sum remains what we call now the CHP sum, summing over 6 bonds remains the constant. We also did it, for example, for 3D, D0 systems. And then we have one outlier, lanthanum 203, where there was an increase when we found out there was a big structural change. So if there is no structural change, or we have a D0 system, the sum remains constant. If there is a big structural change, we see the steady increase. So that allows us to again explain basically the outliers here. They must be due to the not changing COHP, and really for these, the COHP should not be this high level value from the bulk, but it should be really 0. And that would put them all the way to the left of the plot. So this was started with my new postdoc Neha, who is also, I believe, part of the Zoom session. And so we start looking into these differences in COHP between the active sites before and after absorption. And we call this quantity change in the COHP, and see whether this could be the descriptor we are after. So actually, how does it look like in real calculations? You can see here one example, for example, hafnium 110 surface, as you are changing the absorption of this active site over here. So you're starting from empty to O to OH. You can see that there are small minor changes. And this system is again D0. So this COHP sum is changing a little bit, but also the surroundings of the catalyst also responding to the absorption. And that has to do like due to the rearrangement of the bonding itself in the system itself. And so this is kind of like a generalized Bader diagram, where you, rather than using Bader charges, you are using COHP to quantify amount of bonding for each transition metal center in the system. So basically, we concluded that this is not enough. And many systems, when there's a large structural change, we have to expand the sums to second order, third order, and fourth order to fully capture the evolution of the system at the absorption. And so some systems converge very fast, but some systems are very peculiar, and they have a kind of it takes a long time before the COHP sum kind of converges to the steady state. So then we took these values, extrapolated to the kind of a large limit, long distance limit, and then we plotted them here as a function of series for the oxygen-associated energy for 110 surface for the rutile series. You can see it here, and this is the actual absorption energies. So if you look left and right plot, you can see that this descriptor, which is not explicitly an energy-based descriptor, leads to very good qualitative and quantitative agreement with the absorption energies on these transition metal oxides. And very importantly, it also captures the D0 dependence at titanium, zirconium, hafnium. Now, it's not all perfect because you can see that 3D contribution for CHP is a little overestimated. But overall, we are very happy with this finding, and we are still trying to find a different kind of normalization schemes where why is this happening for this high spin 3D elements, why it is actually adding the CHP so much more contribution than it should. So, but we decided that let's go bigger, let's try even a bigger data set. So what we did here, we did a survey of all the transition metal oxides of the basically 3D, 4D, 5D. You can see of the group 3 all the way to 14. And we focused particularly on the systems which occur naturally and have an octahedron as a building block, because we have had an expectation that octahedral systems will have similar behavior, and now we're also focusing on octahedral systems. And you can pick a single element, for example, molybdenum. So what we found out that actually molybdenum will never have a +2 oxidation state, but it will likely have a +3, +4, +5, and +6. And when it's like kind of a bright outline, it means that there is an octahedral structure available, and also when it's colored means being good data set. So we, again, for each of the oxidation state, we have to choose a particle polymorph. So as I told you, for +4, we choose only rutile polymorph, which is a limitation, but it's sufficient, we believe, and I can explain discussion why. And then for +2, we to Grox cells, for +3, corandrums, etc., etc. You can see here. And simplified MO3 group for here for +6. So this was a very big effort. We worked kind of like a whole year after COVID on this. And here is the revealed result. So you can see here that around this was basically this data set was converged basically mostly on Benjamin with help of Neha and Kirsten and myself. So you can see the plot here that for 5D elements, the behavior of +2 to +3 to +4 to +5 to +6 is steady increase. So as you increase the oxidation state, you are actually you're kind of climbing up to the weak and weak absorption energy, and you're moving this minimum, which was previously at 4 to 5 to 6 to 7 and so on. So the D0 minimum is moving because you are oxidizing more and more the active site. And we are still getting the same weak binding regime and at basically at D0 and D10. Although for some of them we stopped, so you can see some of them do not exist. So for example, +6, we only have several points. We don't have the whole series because they simply do not exist. They are very unstable. For 4D series is actually very similar. And the only difference is that it's slightly weaker bonding. And for 5D, for 3D, they exist also in +2 oxidation state, which the 4D and 5D do not actually surprisingly prefer to be in +2 oxidation state. And you can see now the formation of the high spin and low spin minimum. So as you can see, the 4Ds and 5Ds, again, they never have this high spin minimum, they only have the low spin minimum. So this is very interesting. And so we now said, and additionally, we were kind of asking ourselves, is it true that in chemistry, the diagonal rule, as you're moving down going periodic table, do I get kind of a same reactivity, right? This is do the elements kind of repeat themselves? And I would say that actually this plots kind of predicted that if I'm moving from maybe vanadium towards molybdenum towards rhenium, it's kind of there. So it has very similar reactivity. So this data set will be soon released at Catalyst Hub, and it will be available for various machine learning and testing the approaches. But what we did is, of course, we calculated COHP for the systems. And when we did that, this was the result. So it turns out that if you consider a variety of oxidation states, variety of structures, you need to perform some sort of a normalization at the bulk level. And then you can predict the absorption energy with relatively good accuracy, but this is not enough. You have to build basically simplify machine learning model, where of course the COHP is the main descriptor, but also the oxidation state is a part of the description. So you have to tell the machine learning what is the formal oxidation state of that bulk system and what is the COHP of that bulk system. And are there any equivalent bonds? So this is actually average COHP across all the bonds in the octahedron. And when we did this, actually, team led by Kirsten and Benjamin, so they found out that it's actually possible to create very easily a model which predicts the absorption energy with this predictor, which is mostly weighted on COHP oxidation state, with a very high precision of only 0.23 eV in absolute error, which is, as far as we know, is the large data set of transition metal oxides with the smallest possible error in prediction of the absorption energy. So this manuscript we now wrapping up, and we are just doing final touches before we submit this. And we were very excited about this. So using simply just the bulk COHP energies for variety of transition metal oxides, it's possible to predict the absorption energies with qualitative and quantitative agreement with the true absorption energies. So in summary, in this, I showed you that we had set to study reactivity trend in transition metal oxides. And when we studied Rutal series, we found out that, in fact, there is the descriptor of absorption COHP closely resembles the absorption energy. And you can already extract it at the bulk level and only misses the D0 and D10 kind of occupations. And those we had explained with COHP sums, so summing over the larger region of the COHP. This is the first theory which is enables to unifying the descriptor theories based on d electrons and descriptor theories based on p electrons to a single theory, which sums up the contribution, basically its overlap between d electrons and p electrons into a single number. And when we performed the large analysis for the large data set and acquired the COHP bulk values for large amount of oxides, we found a very good qualitative and quantitative prediction for the absorption energy of the whole data set. And so the COHP is not new. There are many people who are using this, and it was actually, there is also a quick bonus application. I want to show it to you that it's not unique just for transition metal oxides, and it's not just for the absorption energies. It can be used also for formation energies. And so, for example, we had a study in 2022. In collaboration, we have a visiting student, Jacqueline, who just graduated from MIT, from Yangshan Horn, where we actually look at the series of alkaline air metal oxides for basically replacing oxygen evolution reaction with metal oxygen evolution reaction. And in that reaction, it's crucial to understand overall thermodynamics of these metastable species in alkaline air metal oxide. So you can see we are going from lithium 2O to lithium 2O2 to lithium O2. And what you see in the background is the heat map of the overall stability of this transition of this oxide. These are alkaline air metal oxides, right? And you can create a kind of a ternary map where you can use the COHP to measure basically covalency of this metal oxygen bond along this axis, which strongly correlates basically with this absolute oxidation potential or stability of the system. So basically, the more COHP you achieve in the system, also the more stable these particular oxides will be. And this can be extended, also study a variety of perovskite systems and non-oxide systems, etc., etc. So with that, I will just conclude or basically acknowledge our group. So again, I am very thankful for everyone contributing to this work, and also the SUNCAT. Majority of this work was done by Benjamin, Kirsten, and Neha. And also we have Frank help with the useful advice on the development of theory, and DOE for funding. And please keep eye on the Catalyst Hub org. We are releasing all these accurate data sets. And with that, let me also bring to your attention one more thing, that we will be organizing this summer a SUNCAT Summer School, where you can live. We have a variety of conference invited speakers, and you can hear the latest about the computational theory, computational catalysis entered, and also experimental catalysis. And there's actually a few open spots left, so please don't hesitate and Google this link over here, SUNCAT Summer Institute, and registration is actually not that expensive, and we would love to see you in person at Stanford this summer. Thank you very much.